The morning sun, a lamp lighting up a dark room, and even the screen you're looking at right now. We can see everything around us because there is light. Strictly speaking, we don't see objects themselves. We see the light that bounces off them. In other words, without light, we wouldn't be able to see anything at all. What exactly is light that it fills our world so completely? Or does it even fill it? Is light a kind of matter? By common sense, matter must have a physical presence, but light has none. Light doesn't have mass. Even invisible air has mass, but light does not. This mystery of light has puzzled people since ancient times. Ancient Greek scholars like Euclid and Ptolemy believed that rays shot out from our eyes, allowing us to see objects. Aristotle believed the sun was the sole source of light, and that light traveled as a wave through a medium. Debates over the true nature of light continued into the 17th century, and then came one scientist who changed everything: Isaac Newton. Using a prism, Newton discovered that white light is made up of multiple monochromatic lights. He argued that these were made of tiny, invisible particles. But Newton's particle theory couldn't explain everything about light, because light also flows like a wave. Scientists like Huygens also proposed this wave idea, but their theories were overshadowed by Newton's influence. But nearly 180 years later, someone brought the wave theory back: Thomas Young. He conducted one experiment using light. He shone light through a board with two narrow slits in it, the famous double slit experiment. If Newton's particle theory was right, some would hit the wall and bounce off, while others would pass through the slits and leave two clear lines on the screen behind. But instead of two lines, multiple lines appeared on the screen. This could only happen if light wasn't a particle, but a wave. When waves interfere with each other, they create patterns like this. From this experiment onward, the wave theory began to gain new attention. In the mid-19th century, British scientist James Clerk Maxwell discovered that light is a type of electromagnetic wave, a wave generated by electric and magnetic fields through his landmark Maxwell's equations. These equations describe how light moves with such clarity and elegance. Electric field and magnetic field, oriented perpendicular to each other. An oscillating electric field causes a magnetic field to oscillate, and the oscillating magnetic field causes the electric field to oscillate again. Like a dance, these rippling fields generate each other in a chain reaction, propagating through space as electromagnetic waves, what we call light. Some scientists even called Maxwell's equations a blueprint from the hand of God. Just as the wave theory was becoming firmly established, a new shift emerged: Albert Einstein. Einstein's 1905 paper on the photoelectric effect raised new questions about the nature of light. The photoelectric effect is a phenomenon where electrons are ejected from a metal surface when light above a certain frequency strikes it. But this couldn't be explained if light were purely a wave. Einstein resolved this paradox by proposing that light is made up of quantized particles called photons, which collide with the electrons in the metal, perfectly explaining the effect through the particle nature of light. This led to the conclusion that light behaves as a wave and, at the same time, acts like a particle when interacting with matter. Light has wave-particle duality. This marked a paradigm shift, the idea that a single entity could possess two contradictory properties at once, and a paradigm shift inevitably gives birth to new questions. Could it be that not only light, but other forms of matter also exhibit both particle and wave behavior? This was the birth of the matter wave theory. According to French physicist Louis de Broglie's 1924 paper, all matter exhibits wave-particle duality. And when we say all matter, that includes us, human beings too. Does that mean we too might be waves? Yes, but because we have a much larger mass, our wavelength approaches zero according to de Broglie's equation. That's why our wave-like property doesn't manifest. In other words, the smaller the mass, the more pronounced the wave property becomes. Does that remind you of something? Quantum mechanics. The matter wave theory gave rise to quantum mechanics, a field dedicated to studying the strange behavior of particles like light and electrons in the realm of the very small. In the end, the strange phenomena observed in light turned out to be a result of how particles behave differently in the macroscopic and microscopic worlds. But in truth, when we call it duality and say that light behaves differently across those worlds, we're really just applying a human perspective. We were the ones who arbitrarily drew that line. Do you agree that the Earth is round? If the Earth is round, then why does the ground beneath our feet seem flat? If we think of the Earth as a two-dimensional circle, then when the circle is large enough, its curvature becomes so small that one section appears almost like a straight line. That's the macroscopic world we live in. But what happens if we zoom in? If we zoom in on one part of the circle again and again, it looks like a straight line once more. This is the microscopic world. Circle and line, macro and micro, wave and particle. It's all just a matter of perspective. After all, they are one and the same. So far, we've only discovered a few of light's properties and behaviors. We still have have no idea where it came from, how it began, or what it truly is. But one thing is certain, just as countless scientists have advanced science by exploring light, even now, light continues to connect us to a world we do not yet understand. Someday, more of light's unknown properties may be discovered. And when that time comes, we should not be too surprised. Because after all, now, as always, it's just light.